So, hello everyone. Welcome to the second live session of this course, which is Wave Updates. So, I'm Gitanjali. I'm the PhD scholar from IIT Delhi, and I'm the PMR FTA for this course. So, in the last lecture, we have gone through some of the basics of wave optics, like wave equation, different types of wave, and what are the different expression of different type of wave, plane wave, spherical wave, or cylindrical wave. So in this week, so before starting the session, let me know whether my voice and the screen is visible to all of you. Let me know, then we'll start the session and start solving uh, the problems related to the week two. Okay, so if it is clear, then let me start. So in this week, we have basically deal with what will happen when we superimpose different type of waves, which have same frequency or which have different type of frequency. And then we move towards the discussion part, and the in the lecture basically it discusses what are the what will happen when we have material dispersion in the medium, and what are the different equation for that material dispersion. Okay, so let me briefly go through the content. So to for the superposition, so now we are just dealing with the superposition of scalar wave. So we are not dealing with the vector wave. So we are just dealing with the waves that have either they have same plane of vibration. They are either parallel or antiparallel. Okay, so we are basically dealing with only one component of electric field. So for this superposition, so we have three different method that to find out what is the expression for the composite wave after the superposition. So first is the algebraic method, and second that we have seen is the complex method, and the third one is the phasor addition. So for algebraic method, what we do, we express each electric field or magnetic field wave is EJ0 cos AX j minus omega t plus phi j. So we express it as a harmonic wave. In complex, we express the same expression in terms of the complex expression. So EJ is now the complex part, EJ0 e to power I k xj minus omega t plus phi j. In phasor addition, what we do, we represent this complex wave in a complex plane where this the horizontal axis is the real axis and the vertical is the imaginary axis. And for a given wave, we draw this arrow, and this length represent what is the magnitude. Let's say this is E10, and this angle, it is the phase angle. Let's say it is phi 1. And for the second wave, what we do, we take a horizontal and rotate it anticlockwise according to the phase phi 2. Then we draw the what is the amplitude of second wave. And the resultant will be the arrow which is from E1 to E2. And this is the angle phi for this composite wave. Okay, I think one of you have one question. We use complex method when there are more than two waves to be superposed, right? Yes. Complex method, you can use it when you have more than two or three or four, because there it's kind of the mathematics is kind of simpler. So that is why. So it's according to your like what you are comfortable with. If you are comfortable with algebraic method, then it's also possible to use algebraic also, but it will be become a linear one. But you can use complex or phasor addition according to your whatever you are comfortable with. But if you look at the result of this, all these three kind of superposition method, so they show the same results. Like if you want to represent what is the expression for the electric field, let's say after superposing all the wave, we have one resultant wave ER, which we express as E0 cos omega t plus some phi. So let's say alpha. So for all this method, we found that we have E0 square. We can write it as summation of EJ0 square from J1 to N. N is the number of wave we have in the independent wave we have in the system, plus the cross term, which is 2 times J greater than I from 1 to N, E JO EIO cos alpha j minus alpha I. So this is to find out what is the amplitude of this wave and to find out what is the phase alpha. So we have tan alpha, which is summation E J0 sin alpha j from 1 to n divided by summation J1 to n EJ0 cos alpha j. So all these methods, they have the same fundamental relation. So whatever method you choose, you will get same expression. Okay. Okay. So from this, what we can guess is that after when we combine different type of wave of same frequency, we get the composite wave. They have the same frequency. Frequency doesn't change after when you combine all of them, but the amplitude as well as the phase, it may or may not change. Okay, so this will change alpha and E0, but omega will remain as it is. It is equal to what is the frequency of the constituent wave. So in this expression, you can see, so these are the interference term. And from this, you have, so the final amplitude, it depends what is the value of alpha j minus alpha I. So this we call it as, this is the phase difference that we have in the system. So phase difference is, let's say we have two waves. So phase difference, we can write it as alpha 2 minus alpha 1. So this is, recall alpha is the time independent part. So it is kx2 plus alpha 2 minus kx1 plus, sorry, phi 1. So this we can rearrange it. So this is kx2 minus x1 plus phi 2 minus phi 1. So the phase difference, that is the interference term, it depends on the term which is, so the difference in, this is the difference in path transfers by this two waves, E1 and E2. And this is the difference in the initial phase angle. Let's say we have initial phase angle is 0, then the phase difference will be only the, what is the difference in path, kx2 minus kx. So k, we know this is 2 pi over lambda. So this is x2 minus x1. And lambda, we can write it as lambda 0 by n, free space wavelength divided by refractive index. So 2 pi over lambda 0 n x2 minus x1. So this term n x2 minus x1, this is the optical part difference. So this we define it as a optical part difference. So uh, so next what we have seen. So these are different type of method to find out what is the expression for the final composite wave. What is its amplitude and what is its phase angle. So afterwards, what we have seen there are depending on the phase, initial phase, we can have two types of sources. One is where the source have randomly oriented phase, and other is the sources where we have coherent source. That means the phase difference, it doesn't vary from time to time. So this from this, what we have seen they have different type of intensity pattern. So source is one is where we have randomly phased source. That means the phase difference phi 2 minus phi 1. They are not constant. They are not in phase and they vary from time to time. So for this is the one case, and the second one is the coherent source, where this phi 2 phi and phi 2 minus phi 1, they are in phase and they do not change from time to time. So there are different example of coherent source and randomly phased source. So for the first one, randomly phased source, if you recall, for this case, because the phase are varying from time to time, so the interference term, which is 2 summation j greater than I from 1 to n, e j o e I o cos alpha j minus alpha I. So because these are varying from, they are randomly varying, that means the average will be 0. So that means this summation will vanish, and whatever the final amplitude we have is E0 square is summation of E J0 square from I to 1 to n. And if so, this will give n times E square, assuming that they have the same EJ0 for the n source. But for if you look at the coherent source, so for the coherent source, they are in phase. So that means this interference term is not 0. So for that case, we have E0 square. This will be, I'm writing the final one. So this is from J1 to N, E J0 whole square. So this will give n square times EA square. So and we know that intensity is directly proportional to amplitude of electric field. So that means for randomly phase source, we have intensity, which is proportional to n times EA square. And for the coherent source, we have intensity, which is n square times EA square. So if you take a coherent source and if you take a randomly phase source, then you will get different type of intensity pattern for these two sources. And for coherent source, the intensity is much larger than the intensity of randomly phased source. Okay. So after that, what we have seen a special case of standing waves. So what is a standing wave? So it's not a traveling wave. It's uh, it's just a wave that is propagating or that is oscillating in space. So for this, what are the condition we have for standing wave to form? So we have two counter propagating wave. One propagating in the positive direction, and another one is propagating along the negative direction. So let's say E1 is E0 sine kx minus omega t, and E2 is E0 kx plus omega t plus some initial phase phi. From this, after combining E1 and E2 and doing some algebraic manipulation, so we get that this we can express it as a 2E0 sine kx plus phi r by 2 and cos omega t minus phi r by 2. And when phi r by 2 is 0, so we simply have here is 2E0 sine kx cos omega t. So this is quite different from the traveling wave that we had earlier, which is of the form of which is the function of x plus or minus vt. So for this standing wave, let's we saw what are the nodes and what are the antinodes of this wave. So nodes is where the total amplitude is 0 and antinodes is where the amplitude is maximum, either in the positive direction or in the negative direction. So for nodes in spatial part, so if you see it depends on x, and because k is 2 pi over lambda, so if x is, let's say we have 0, lambda by 2, lambda, 3 lambda by 2, then we will get nodes in the system. And for x is lambda by 4, 3 lambda by 4, then for this case, we will have antinodes in the system and the maximum amplitude will be plus or minus 2E0. Okay, so this is about the standing wave. Afterwards, what we have seen, I think we have seen what will happen when we superimpose two waves of different frequency. So for this situation where we see that we have carrier wave and the envelope wave, and we have the concept of phase velocity and the group velocity. So superposition of two waves of different frequency. So we started with the same harmonic wave. E1 is E10 cos K1x minus omega 1t, and E2 is E20 cos K2x minus omega 2t. So when we combine this E1 and E2, so we find out that we can write it as 2, let's say E10 and E20 are same. So we have 2 E10 cos K1 plus K2 by 2 x minus omega 1 plus omega 2 by 2 t. Then we have cos K1 minus K2 x by 2 minus omega 1 minus omega 2 by 2 t. So in this expression, we have different type of frequency, angular frequency and the wave number. So this K1 plus K2 by 2, this is, we call it as, this is the average propagation number. Let's say we denote it by Kp. And we have average angular frequency, which is omega 1 plus omega 2 by 2. This is omega p. And in next term, we have the modulation frequency. So we have omega g is omega 1 minus omega 2 by 2. And kg is k1 minus k2 by 2. So this is the modulation frequency, and this is the modulation propagation number. So from this, what we have graphically seen how we can represent this resultant electric field. So which is 2p10 cos kpx minus omega pt and cos kgx minus omega gt. So this we call it as the carrier wave, which have different frequency component, and this will call it as the envelope wave. So for the carrier waves, these are the waves which have average frequency and the average propagation number. And the velocity of this carrier wave, we call it as the phase velocity, which is given by omega p by kp. And for the envelope wave, we call it for the part which have the modulation frequency as well as the modulation propagation number. And the velocity of this envelope wave, we call it as groove velocity, which is omega g by kg. And from the expression, we can easily see that these are average frequency and these are difference in frequency. So in general, the phase velocity is larger than the group velocity. Okay. So from this, we can graphically show this carrier wave as well as the envelope wave. So this is the envelope part, which is propagating at group velocity. And in each envelope, we have the carrier wave, which are propagating with the group velocity. So this we see whenever we have waves of different, when we combine waves of different frequency, and this is the most realistic situation, because if you consider a source, it's not like it emit at a particular wavelength or particular frequency. They have a frequency wavelength spread, so they have a bandwidth. So for the real situation, this is the realistic representation of the waveform. Okay. So this is the envelope part, the dotted one, and this is the carrier. So from this, you can easily see they have the different frequency, the different phase velocity and the group velocity. So because of this difference in the speed, we'll see dispersion in the medium. That means whatever wave we are incidenting on a medium or we are feeding to a, let's say, optical element, in the output we'll see a different type of wave. It may be compressed or it may be spread out because of this different the dependence of phase velocity, the difference in phase and the group velocity, and the dependence of refractive index on the wavelength. So to quantify it, what we have done is that first we have seen what are the relation between this phase and group velocity. So Vp, we have, this is omega by k, and group velocity is d omega over dk. So from this, we can say omega is k times Vp. So we can put it here. And we got one expression of Vg is Vp plus k dVp over dk. So you can consider a situation where this is zero. So for that case, Vg is Vp and we don't have any dispersion in the medium. But for practical situation, this is not zero. It can be positive or it can be a negative quantity. So for a dispersive medium, we have the phase velocity, which is omega by k. This we can write it as c by n of k or n of omega or n of lambda, whatever you are comfortable with. So Vp is c by nk. From this, we can write Vg is Vp plus, I think it was Vp 1 minus k by n dn by dk. Or in terms of lambda, by using k is 2 pi over lambda, we saw Vg is Vp 1 plus lambda by n dn over d lambda. And in general, for a medium, the refractive index is not constant for all the wavelength. So the refractive index, it varies according to the wavelength of this of the source. So because of that, we'll see, because dn over d lambda is not zero, that means we see that the groove velocity, it is a function of wavelength. So this gives rise to what we say is the material dispersion. And to find out how the refractive index depends on wavelength, I think you can recall in the lecture we have used the Lorentz model of dielectric to find out what is the dependency of n over lambda. So I hope that model is clear to you. If not, let me know. Okay, so I'm just writing what are the expression that we got from the model. So using this model, we got n square lambda is 1 plus summation ai lambda square minus lambda square lambda I square. So lambda is the wavelength, different wavelength, and lambda is the resonance frequency. And the summation is over I. So if you consider a situation where lambda is much, much greater than the resonance. So we are not in a region where lambda is close to this resonance frequency where the refractive index varies rapidly. So we are in a region where lambda is far from this resonance frequency. So for this case, this equation, we can simplify it. So this simplified to the Cauchy's equation, which is A plus B by lambda square plus C by lambda per 4. Okay. So graphically, we can say this is how the refractive index depends on the wavelength. And using this dependency, we can see how the material dispersion affect and how to find out a wavelength where this material dispersion vanishes. How to find out this particular wavelength, which we call it as a zero dispersion wavelength. So we'll see one problem on that. So I think up to this concept, this will cover whatever the questions that has been asked in week 2 assignment. So in our next lecture, we'll see see what are coherence and what are the different conditions for that. Okay. So let me know whether you have any doubt till now. Uh, if not, then we'll move to solving the problems related to this week. Um, okay. Laser addition can be done when two waves have the same angular frequency. Yes, it can be done when we have the same angular frequency, because for phasor addition we are not taking into account the omega t part. So we are assuming that omega t is the baseline, which is the horizontal line. So if you are considering the phasor addition, I think it will be useful if you have only, let's say, two or three waves. But if you have more than two or three waves, then it will be difficult to find out the final expression. And also, the if the frequency is different, then it's quite difficult to because represent it in the phasor. So if you have same frequency, you can consider the phasor. Like what I'm saying is that for phasor, if you recall, this is the real part. This is the imaginary part. In actual case, the phasor is most, it is best represented by, we take omega t is a baseline. Then on the base, we represent the whatever vector we have. Let's say, or the wave we have, E10. This is at alpha 1. And because the second wave does have the same mm, omega t, so we can represent it here. So what we do is that we don't represent this omega t part, we take it as a 0, that is the baseline omega t. And from this baseline, we represent the E1 part and the E2. But if omega t is different, then the baseline is also different. So for that case, graphically it will be confusing, and maybe you will get wrong answer if you are not careful. So for that case, it's better to take either the complex method or the algebraic method. Okay. So let's move to our uh, problem question and answer part. So in the last lecture, I have gave you, I think, one question to solve it. Let me know whether you have solved or not. It was a easier one. So it's, I think, question number 12. Okay, this is for week 2. So for this question, have you tried to attempt finding the answer for this? So I think, yes, the electric field was given. It was asked to calculate the what is the Poynting vector of this electric field. Okay. Yes, answer is correct. Option is the answer. I think then you must have found out B is. Let me go through the answer in brief. So this is K cross E by omega. So K is here. So K is K Z K. And if you take the cross product, then you got B is K E0 over omega cos kz minus omega t minus 6k minus sine kz minus omega t y. So Poynting vector is easy to find out, which is S is E cross H, or for non-magnetic medium, we can write H is B by mu naught. So just put E and B, so you will get S is E0 square mu naught C Z cap. If I'm going to use the S is 1 by I didn't get it. I found, so you have calculated B, then you have used 1 by any. What is E here? Sorry, E is the electric field. Okay. Okay. So 13 number question, we have solved it. 14 is also done. 15 is also done. Okay. So 17 one, we are not able to find out whether it is answer B or C. But one thing I have checked is that it was asking the electric field and the magnetic field of point source, not a point charge. So for point charge, the electric field is inversely proportional to 1 by r square. And one thing also you can uh, easily guess is that a point charge, it it cannot produce a magnetic field. For magnetic field, we either need a current source. If you recall the Maxwell's, I think the fourth equation, the Ampere's law, curl of H is mu naught, not mu naught. This is J plus dou D by dou T. So for magnetic field, we need a current source or we need a time varying electric field. Only then we will get a magnetic field. So because it's a point source, not a point charge, so answer, I think it will be this one. So point source, it will emit a spherical wavefront. And for spherical wavefront, we have electric field, which is, if you recall, electric field for spherical wavefront, it is 1 by r. For cylindrical, it is 1 by square root r. But for spherical, it is 1 by r. So point source, it's like it is made up of many types of point charges. So it's not like, so you can say, what would be the example? So let's say, mm, let's say a dipole. So if you consider a dipole, so it's also a source, but the charge is it's not like it is point charge. So dipoles have two equal and opposite charge. And the dipole radiation or the radiation that is emitted by the dipole, it is quite different from the radiation or the wave that is emitted by a point charge. So this is one of the difference between point source and the point charge. So point charge means only one charge is there, and point source, it is a combination of many charge. So I hope the explanation is clear to you. Okay, so let's move to our next question. So this one is also, I think we haven't solved it. So let us solve it. So there is a plane electromagnetic wave, which is magnetic field given by B is this one. Okay. So I cape, K cape, J cape, these are the unit vectors. K is the wave number. What is the electric field for this wave? Can you solve it in quick? Answer is A. Yes, correct. So the answer for this is A. I think you know what is the formula that you need to use. So this is, so you can use Maxwell's third equation, dou d by dou t, which is dou by dou t, we can write it as minus of I omega, and d is epsilon times. Or for free space, this is epsilon naught. So from this, we found E is minus C kk cross B. B is given, kk we can find out because kk is nothing but what are the coefficient of the spatial coordinate, which is k by root. So kk, this is the unit vector along the propagation direction. So this will be k by mod k. So this will be minus ik plus jk by root 2. I hope you can easily find out this. You can use it here and the magnetic field, and the final expression will be option A. Okay. So let us move to our next question. So for this question number 18, what is the average Poynting vector? So electric field was given, magnetic field is also given. Let me write. mm, So B is C. CB0 IK minus JK by root 2 sine x plus y k by root 2 plus omega t. This is A. B is already given in the question. B0 AK sine x plus y k by 2 plus omega t. Using this, you need to find out what is the average Poynting. So average Poynting vector is yes. So this is the average Poynting vector, or what we call it as a intensity. Finding the intensity of the wave. It's quite easy because you already have the expression of E and B. And if you know the what will be the average of cos square, sine square, then you can easily find out what is the Poynting vector for this case. So first find out what is the Poynting vector, then you can take the average. That what is S? So let me just quickly go through it. So S is E cross H or E cross B by mu naught. So cross, we are taking the cross product. So S would be C B0 square, and the cross product will be between the unit vector I j by root 2 cross k sine square, whatever the term is here. Let's say this is alpha. So this will be CB0 square minus I cap minus j cap by root 2 sine square alpha. So we have this, so we can easily find out what will be the average. So these are constant, so this will be outside the average. We have average of sine square, which is half, right? So this will be CB0 square I cap j cap by 2 root 2. I think there is a mu naught also here. So answer is option D. I think we have two more questions, then we'll move to our questions related to weight. So question number 20. There is a light source which is a small filament at the center of a spherical glass ball of radius 5 centimeter, and it has a negligible thickness. If the source emit 100 watt of power in the form of spherical electromagnetic waves, the amplitude of electric field will be approximate. So power is given is 100 watt. Question is to find out what is the amplitude of electric field. And it's given, it is the power is in the form of spherical electromagnetic wave. So relate the intensity with the amplitude of electric field. Then you can get what is A0. Yes, answer is the option. Is the answer. So I think you have followed the same. It's fine. Take your time. So I'm just letting you to solve it first because it will be uh, helpful for you also. So it doesn't matter how much time you are taking, but try to solve it first. So intensity is nothing but the average of Poynting vector. So this the expression is half C epsilon naught E naught squared. Power is given and it's also given it's a spherical glass bulb of radius 5 centimeter. So from this, let me know whether uh, I'm writing wrong in any of this expression. Okay. So this is power per area. So we can write it as 4 pi r square. So that means E node is 2p, or let's say we cancel the 2. So this is p 2 pi r square c epsilon. So E node is square root 2p. Sorry, this is p. Let me just put the values. So P is 100 watt. 2 pi. R is, I think, 4 or 5. 5. Well, and 4 pi, sorry, epsilon naught, you can put it as 8.85 into 10 to the minus. So from this, we get a value of A0 is 1.549 into 10 to the 3 volt per meter. So answer is A. So next question. There is an electromagnetic wave in free space which is given by E X Y Z T. This is Z cap E0 cos kx minus root 3 ky minus 2 omega t. What is the Poynting vector associated with this? Okay, so it is asking about what is the direction of the Poynting vector. So here you don't need to calculate what is the value of Poynting vector, but you need to recall what is the uh, in which direction the Poynting vector will align. So if you know that, then you can easily find out the answer. No need to calculate the H, then E cross H. Yes. So the answer is C. So Poynting vector, it is along the direction of propagation. So to find out the Poynting vector, you can see in the answer it is written in terms of unit vector. So you need to find out what is the unit vector along the not what is the vector along the propagation direction. So which is quite easy to find out because here we have A is A by 2 x cap minus root 3 k by 2 y cap. So from this, you can easily see. So this is along the direction of. So if you take the unit vector, so you can find out this is along k cap minus root 3 y cap. Okay. So this will be our last question for week 1. So there is a plane electromagnetic wave which is traveling along the positive z direction. The maximum electric field along the x direction, E max along x, it is 10 volt per meter. What is the approximate maximum value of the power per unit area and the magnitude in the magnetic induction B is given by. So we need to find out what is the maximum value of power per unit area and what is B max. calculate it and let me know the answer. Three point three into 10⁻⁸. Yes, B is correct. What about the intensity? 0.265. Okay, so let us see what will be the intensity. So power per unit area is nothing but the intensity. So this is half C epsilon naught E naught square. So just put the values. This is 8.85 into 10⁻⁻12. E0 is given, maximum amplitude is 10. So I think from this we will get 0.132 watt per meter square, if I'm not wrong. And for magnetic field, it is E0 by C, the maximum value. E0 is given 10 and C is 3 into 10 to the 8. So this will give 3.3 into 10 to the minus 8 Tesla. Okay, so let us move to our questions that is related to, but intensity is not maximum P by. So power per unit area, it is nothing but the intensity. So if the question is asking about what is the maximum power per unit area, that means indirectly it is asking about what is the intensity of the wave. So don't get confused between average Poynting vector and the intensity. So intensity is the average of Poynting vector, not the other. Okay. So I think you are taking, this is the average intensity. So this is not average intensity. This is the total intensity, which we got after taking the average of Poynting vector. So I hope it is clear. Okay. So let us move to our question set, which is related to the concept of weak 2. So we'll start problems that is more and less similar to the concept of week 2, also similar to the concept that has been asked in the assignment. Okay. Is the questions visible to you? I think the letters are the letters visible? Okay. So the first question is the speed at which short wavelength ripples travel over the water. It is given by it is 2 pi gamma lambda rho. So gamma is the surface tension, rho is the density. These are constant. So for this ripple, you need to calculate what is the group velocity of this ripple. So let me give you 3 minutes, calculate it, and let me know the answer. It's quite easy. Just recall what is the expression for the group velocity that we have seen in the lecture. And relate the group velocity with the expression that is given here. Yes, the answer is option D. So given this is the speed, so this is the phase velocity, which is omega by k. So omega by k is 2 pi gamma by lambda. So 2 pi over lambda, it is nothing but k, right? K lambda by rho. So that means omega is k square root k gamma by rho. And if we recall the group velocity, it is given by d omega over dk. So that is why we express, we find out first, we find out what is the expression for omega in terms of k. So after that, we can take the derivative. So that means this is d dk k k lambda by 2. So this will give 3 by 2 square root k gamma by rho. This is the phase velocity that we had earlier, 3 by 2 v. So group velocity is 3 by 2 times v. So next question, it's a conceptual one. In a non-dispersive medium, the phase velocity Vp and the group velocity Vz are related as. For the non-dispersive medium, what is the relation between phase and group velocity? Option A, Vp is half of Vg. Option B, Vp is equal to Vz. Option C, Vp is 2 times of Vz. Or option D, Vp is 3 times of Vg. Yes. For the non-dispersive medium, both the velocities are equal. This we can easily guess it from the expression also. So recall Vz is Vp 1 plus lambda by n dn over d lambda. So for non-dispersive medium, this is 0. So Vp is equal to Vz. Question number 3. Which of this following statement is not true? The group velocity is smaller than the phase velocity in the region of normal dispersion. Option B, the phase velocity is greater than the group velocity in the region of anomalous dispersion. Option C, the wave travel with same phase speed in a non-dispersion medium. Or option D, the refractive index of a optical medium increases with frequency for normal dispersion region. Which of this following statement is not true? So it is, question is all about the dispersion. What happens in the normal dispersion for the phase and group velocity? How the refractive index change? for a normal dispersion or for a anomalous dispersion? Okay. So let me go through the option one by one. So recall we have Vg is Vp 1 plus lambda by n dn over d lambda. So this is the general expression that we have seen and we have derived in the class. So for normal dispersion, and we have also seen the graph between n and lambda, which is this. Okay. So for normal dispersion, what is the condition we have? For normal dispersion, dn over d lambda is less than 0. So if we put it here, it is a negative quantity. So that means Vb is Vp 1 minus lambda by n dn over d lambda. So for normal dispersion, Vg is less than Vp. So in normal situation, we have phase velocity which is greater than the group velocity. So options A is saying the group velocity is smaller than the phase velocity in the region of normal dispersion, which is correct. Okay. So option B, the phase velocity is greater than the group velocity in the anomalous dispersion. So let us see the anomalous part. So for anomalous dispersion, we have dn over d lambda. It is greater than 0. So that means Vg is Vp 1 plus lambda by n dn over d lambda. So for this case, Vg is greater than Vp. So group velocity is greater than the phase velocity. But in the question, it is saying the phase velocity is greater than the group velocity even in the anomalous dispersion. So that means this is not correct. So let us see option C also, because in question it may happen more than one question is also correct. Also maybe the answer to this question. So always check all the options. So option C is the waves travel with same phase speed in a non-dispersive medium, which is correct. Non-dispersive, dn over d lambda is 0, so they travel with same phase speed. Option D, the refractive index of a optical medium increases with frequency for a normal dispersion rate, which is also correct. So if you look at the graph where dn over d lambda is less than 0, so this is the graph. So for this case, if you see, as we increase the wavelength, the refractive index decreases. So that means if you increase the frequency, the refractive index will increase. So if you trace the path in this direction, which is along the direction of frequency, refractive index will increase. So option D is also correct. So answer will be option B. This is not the correct statement. So is it clear? Okay. Question number 4. The superposition of two parallel waves. So it's given E1 is E10 sine omega t plus epsilon 1. E2 is E20 sine omega t plus epsilon 2. Given omega is 200 pi, E10 is 8, E20 is 10. Epsilon 1 is 0, epsilon 2 is pi by 3. So If you superpose these two waves, what will be the expression for this final resultant? C. Yes. Answer is option C. This is quite easy because you have only two waves, right? You can easily neglect this two option D because it has 150 pi t, because when you superimpose two waves of same frequency, the resultant wave will also have the same frequency. That means this we can easily filter. So the next thing is the what is the amplitude and the phase. The phase is same in the question. You can see the phase is same. So that means you don't, to verify the answer, you don't need to calculate what is the phase. You just need to verify what is the amplitude. So in this way, you can quickly solve the problems. No need to calculate the phase, but you can also verify the phase whether it is coming right or not. Okay. So our main task is to find out what is E0 because phase are same in both the option. So E0, if you recall, E0 square is E10 square plus E20 square plus 2 E10 E20 cos epsilon 2 minus epsilon 1. So all the things are given. It's 8 square, 10 square plus 2, 8, 10 cos pi by 3. So this will give 244. So E0 is square root 244, which is 15.62. Okay. So that means answer is option C. For the phase, you can easily verify. So 10 epsilon is E10, sine epsilon 1, E20, sine epsilon 2, cos epsilon 1, E20, cos epsilon 2. So epsilon 1 is 0. So that is why this term vanishes. So we have 10 sine pi by 3, 8 plus cos pi by 3. So this will give tan inverse 5 root 3 by 30, which is 33.67. Okay. So this is just to verify whether the phase is same. Okay. So the next question, we have a electromagnetic wave of angular frequency omega. It is propagating in a dispersive medium with refractive index n is n of omega. If the speed of light in vacuum is c, and what is the group velocity of the electromagnetic wave in the dispersion medium? So take the definition of the group velocity and find out how you can relate that to this. Option B. Okay, so let me go through the steps first. So Vg is d omega over dk. So we know that this we can write it as 1 by Vg is dk over d omega. So k is 2 pi over lambda. So we need to express in terms of n of omega so that and dk in terms of d omega. So k is 2 pi over lambda. This we can write it as 2 pi over lambda 0 n, or this is k0 n of omega, or k0 we can write it as k0 is omega by c n of omega. Okay. So that means 1 by Vg, it is d of d omega, omega by c n of omega. So this is 1 by c n of omega plus omega dn over dn. So that means Vg is c over n of omega plus omega dn by dn. So answer is option A, not B. So do you have any question in this problem? Do you have any doubt? Okay, sure. Okay. So let us move to, so instead of solving question number 6, I think it's better. Let's first solve the question number 7. Okay. So it will take some time because this part is not covered in the lecture. So let me solve it first. So there is a material with refractive index approximately given by n of lambda 0 is C0 minus A lambda 0 square B over lambda 0 square. So this equation is valid between wavelength 0.5 micrometer to 1.8 micrometer. And the value for C0 is given. C0 is 1.521, A is 0.004, B is 0.005, and this unit, this is minus, this is square. So lambda 0 is also in micrometer. So the question is asking what is the zero material dispersion wavelength and what is the difference in phase and groove velocity of this material. Okay, so let me go through it one by one. So first is to find out what is the zero material dispersion wavelength. So if you recall the lecture, the material dispersion, it happens because the different wavelength component, they travel with different groove velocity. And why is that? It is because of the refractive index. It depends on the wavelength. So because of this dependency of refractive or index over wavelength, the groove velocity now becomes depend on wavelength. So because of this, we see material dispersion in the medium. So to quantify this material dispersion, so what will happen in this material if we have a material dispersion? So practically what happens is that if we have a pulse like this, then after going through this dispersive medium, uh, the pulse may broaden. Okay, it may become this because of the dependency of groove velocity on wavelength. So to quantify this broadening, we define a parameter. So I'm not going into the details. I will just cover that part that will helpful for you to solve the assignment. Okay. So to quantify this material dispersion, that is the broadening in time. So this we say this broadening, let's say we can quantify this broadening by some delta tau. So delta tau, this we can write it as d tau over d lambda over delta lambda. So we're taking lambda because it depends because of this wavelength dependency, we are getting the broadening. So that is why I am taking the derivative with respect to lambda. So our task is to find out how the tau depends on groove velocity and how we can calculate this value. If we can calculate this value, then we can find out what is the wavelength at which we will get a zero dispersion, zero material dispersion. So let us see one by one. So tau, it is nothing but the time. So tau is time. So time is, we can write it as distance over velocity. So let's say the medium, that is a dispersive medium that we are considering. This is the dispersive medium. This have a length of L. And the pulse that will propagate inside the medium, this is a velocity of groove velocity. So that means tau, we can write it as L by Vg. Okay. And Vg, we know 1 by Vg is dk over d omega, right? And this, the expression that we got earlier is 1 by Vg, we can write it as 1 by C n of omega plus omega dn over d omega. So this is in terms of omega. In terms of lambda, we can write it as 1 by C n of lambda minus lambda dn over d lambda. Okay. So from this, we can write tau now. Tau is L by Vg. So L by C n of lambda minus lambda dn over d lambda. So this is the time that the pulse will take, or the wave, the wave that will take inside this medium. So to find out the broadening, we need to take the derivative. So delta tau, we can write it as d tau over d lambda over delta lambda. So d tau over d lambda is, if you put this here, this will get L by C dn over d lambda minus dn over d lambda minus lambda d square n over d lambda square. So this term will cancel. We have L by C or minus lambda L by C d square n over d lambda square. Okay. So now we can write down the temporal broadening, the broadening due to the material dispersion. So delta tau is d tau d lambda delta lambda, which is minus lambda L by C d square n d lambda square delta lambda. Okay. So this is the broadening that will happen because of this material dispersion. And the more accurate term for this is, we write it as a material dispersion coefficient. For now, this is no need to remember this. So this is lambda by C d square n over d lambda square. So we divide delta lambda and L in delta tau to get this material dispersion coefficient. So you can see it here that the material dispersion coefficient, it is directly proportional to the double derivative of n with respect to lambda. So that means for the broadening, to get zero broadening, that is to neglect the effect of dispersion, this term should vanish. Okay, so if it is zero, then we won't see any material dispersion inside the medium, and it won't happen in all the wavelength. So it happens only at a particular wavelength. So if you recall, uh, one example that I can give is that the communication in fiber optics, that is the communication that we see uh, in a fiber to get to operate our network or to play the video, we need fiber optics, right? We need the fiber, and inside the fiber the signals are sent only at a particular wavelength where this material dispersion is zero, so that whatever pulse we are sending, whatever information we are sending, it remains unchanged at the output end or at the receiver end. So that is why this wavelength is quite important. Okay, and we will get the wavelength uh, to find out the wavelength at which this material dispersion is zero. We need to see the condition situation where d square n over d lambda square is zero. So this is the condition for zero material dispersion. To find out the zero material dispersion wavelength. Okay. So up till now, is all the concept clear to you? After that, we'll move to start solving the problem. Okay. So in the question, uh, the relation between n and lambda is given. So to find out the zero material dispersion wavelength, we need to take the double derivative. So n of lambda 0 is C0 minus A lambda 0 square plus B 0 square. So that means dn over d lambda we can get is minus 2A lambda 0 minus 2B lambda 0 cube. The second derivative is minus 2A plus 6B lambda 0 4. So this should be 0 for zero material dispersion. That means lambda 0 is 6B 2A per 1 by 4. B and A is already given in the question. So this is B, and I think B is 0.005, A is 0.004. So this is 5 by 4. And this will come out 1.4 micrometer. Okay, so this is the zero dispersion wavelength. So in the next part, it was asking what is the phase and groove velocity at this zero dispersion wavelength. So let us see. So for phase velocity, we can follow the definition. So we paste C by n lambda 0, which is C by C0 minus A lambda 0 square plus B by lambda 0 square. C0, A and B are already given. Lambda 0 we have already calculated. And C is the speed of light. So this is C over 1.521 minus 0.004 multiplied by 1.4 square plus 0.005, 1.45. So you will get a value around C by 1.5 for the phase velocity. For the group velocity, you can use phase is C by n lambda 0 minus lambda 0 dn over d lambda 0. So you just need to put the expression. Okay, dn over d lambda 0 we have already calculated. This is the expression. So put it. So you will get C0 plus A lambda 0 square plus 3B over lambda 0 square. So put the value of C0. This is 1.521 plus 0.004, 1.4 square, 3, 0.005, 1.4 square. And this will be C by 1.536. Okay. And if you want to calculate the difference VP and VZ, this will be C 1.51 minus 1.536, which is quite low. This is C 0.0112C. Okay. So difference is 0.0112C and 1.4 micrometer. So the answer would be option C. So is the solution clear to you? Or do you have any doubt in any of these steps? Okay. So let me solve question number 6 then. Question number 6. Consider the refractive index of a medium n of lambda 0. It is given by n0 plus a lambda 0. While lambda 0 is the free space wavelength, what is the expression of phase and the group velocity in terms of this n of lambda 0? We'll give you some time to solve it then. Yes, answer is option C. I think VP is quite obvious. VP is C by N. So it is given C by N of lambda Z. To calculate VG, you can either directly recall what was the expression of Vg with respect to lambda, Or you can follow the step from the definition of 1 by Vg is dk over dm. Okay. This we need to express in terms of lambda so that we can take the derivative. And from that, we can use k is 2 pi over lambda or 2 pi over lambda 0 enough lambda 0. That means dk by d lambda 0 is 2 pi. Similarly, we can calculate what is d lambda 0 by d omega by taking k0 is 2 pi over lambda 0. This is omega by c, which is 2 pi over lambda 0. So that means lambda 0 is 2 pi c by omega. So d lambda 0 over d omega is minus lambda 0 square by 2 pi c. So just put it and you can get V's is c by n of lambda 0 minus lambda 0 dn over d lambda 0. N is given n of lambda 0. It is a lambda 0 plus n0. So that means dn over d lambda 0 is a. So Bz is n of lambda 0 minus a lambda 0. This is c by n0. Okay, so let us move to our question number 8. So it's given in the dispersal relation for a low density plasma. It is given by omega square is omega 0 square plus c square k. Omega 0 is the plasma frequency and c is the speed of light in phase space. What is the relation between group velocity and the phase velocity? Whether they are equal or Vp is square root of Vg or Vp multiplied by Vg is c square or Vg is square root of Vp. Yes, option C is the answer. So you just need to take the derivative of this equation. So this is 2 omega d omega dk. Omega 0 is a constant, so this will give c square 2k. So just rearrange the terms. So omega by k d omega dk is c square. So this is the phase velocity. This is the group velocity. So phase group multiplies will give c square. Okay. Question number 9. It's given to consider the following wave expression. One is E1 is E0 sine omega t minus kx. E2 is E0 sine omega t plus kx. After superposition, the resultant wave will form a option A traveling wave propagating in x direction with amplitude square root E0, or it's a traveling wave propagating in minus x direction with amplitude square root E0, or it's a standing wave with antinode at x equal to 0 and oscillating in the range of minus 2E0 to 2E0, or it's a standing wave with node at x equal to 0 and oscillating within a range of minus a0 to az. Okay, so to get the range, you need to find out what is the final expression for the composite wave. So what I mean is that we have E1 and E2. So we just need to add these two terms and follow the same steps that has been covered in the lecture. So this is E0 sine omega t, or let's say this is alpha. Omega t minus kx is alpha. This is sine beta. So E0 sine alpha plus sine beta. So this expression have sine alpha plus sine beta. This is 2 times sine alpha plus beta by 2 cos alpha minus beta by 2. And if we put the value of alpha and beta, which is alpha is omega t minus kx, beta is omega t plus kx. So 2 is 0 sine omega t cos kx. So this is 2 is 0 cos kx sine omega t. So from this you can see the maximum amplitude, that maximum oscillation that it can have is 2 is 0. Right? So this is a standing wave, and to find out the node we need to put what is the value at which this kx is 0. And for antinode we need to see what is the places where amplitude is maximum or ER is maximum. This, which is for the case, let's say x equal to 0. This will be 1. So we have ER is 2 is 0 sine omega t. And the maximum value of omega t is 1. So ER will oscillate between, this varies from minus 1 to 1, right? So ER will varies from minus 2 E0 to E0 to 2 E0. So option C is the answer. So is this clear? Okay. So let us move to the next problem. Question number 10. It's quite easy. So there is a wave which is the wave dispersion relation omega k is alpha k square plus beta. Alpha and beta is greater than 0 and these are constant. You need to find out the wave number at which the group velocity matches the phase velocity inside the medium. put beta over alpha. Yes, the answer is correct. So Vp is equal to Vg. Vp is given omega by k, which will be beta by k alpha k. And group velocity is d omega dk, which will be 2 alpha k. So these are equal. That means 2 alpha k is alpha k beta by k. So alpha k is beta by k. So k will be square root beta by. So for this dispersion relation, the wave number for which this phase and group velocity are equal is square root beta by alpha. Okay, so let us move to the next problem. So consider the superposition of three harmonic waves. E1 is event, E1 is 6 cos omega t, E2 4 cos omega t plus pi by 2, E3 is 3 cos omega t plus pi. So the resultant wave can be expressed as for these three waves, if we superimpose, we get the ER is E0 cos omega t plus alpha. So what are the values of omega and alpha here? I think this you can easily solve it. So just I'm just going through these steps in brief. You can cross verify the answers. Okay. So if you recall, to find out the final amplitude, we have E0 square is summation E J0 square, J from, for three wave, this is 1 to 3, to summation J greater than I from 1 to 3, EJ0, EI0 cos alpha j minus alpha y. So from this, E10 is 6, alpha 1 is 0, E20 is 4, alpha 2 is pi by 2, E30 is 3, alpha 3 is pi. So we have E10 square, E20 square plus E30 square plus 2 times. Let us put I1. So I1, E10, E20 cos alpha 2 minus alpha 1. And for I1, we have J2 also. So plus E10, sorry, E30 cos alpha 3 minus alpha 1. Then we increase the I to from 1 to 2. So we have E20. And for 2, we have J3 plus alpha 3 minus alpha 2. All the values are already known to us. So this will be 6 square, 4 square plus 3 square plus 2, 6 into 4 cos pi by 2, 6 into 3 cos pi plus 4 into 3 cos pi by 2. So these are 0. And this will give 36. 16 plus 9 minus 36. So this is 25. So E0 is 5. Okay. So we got 5, but there are two options for 5. So we need to check alpha also. So then alpha is summation over j is 0 sine alpha j summation over j is 0 cos alpha j. So this will be E1 0 sine alpha 1. We write E2 0 sine alpha 2. E0 sine alpha 3 over E1 0 cos alpha 1. E2 0 cos alpha 2. E3 0 cos alpha 3. So we know the values of alpha 0, alpha 1, alpha 2, alpha 3. So just put it and I think you will get a value of 4 by 3. So that means alpha is tan inverse 4 by 3, which is around 53 degrees. So the answer would be option B. Okay. So let us see our last problem. Question number 12. What will be the phase velocity of a freely moving particle having dispersion relation omega is h a square by 2, where omega is the angular frequency, k is the wave vector, and h is the Planck constant. So what will be the phase velocity of this freely moving particle? Yes, no matter what the dispersion relation, phase velocity is always omega by k. Okay, I think question number 13 will take some time, so we'll see in our next live session. But for now, I will give this as a homework. So please write down this equation as a question and let me know the answer in our next live session. Okay. So yes, uh, today I will upload whatever the solution of week 1. For week 2, I will upload in our next live session. Okay. Because for week 2, I haven't covered all the questions. That is why it's better if I upload after solving all the questions. For week 1, I will upload by today. No need to worry. Okay. So let us see one last problem. Question number 40. So the relationship between the group and phase velocity in a dispersive medium, it is given by Vg is Vp plus K dBp over d omega. Given dBp over d omega is less than 0. Then comment on the dispersion property of the medium, whether it is following normal dispersion or anomalous dispersion. What will be the answer for this? Okay, so one thing you need to remember is that for normal dispersion, Vg is always less than Vp, and for anomalous dispersion, Vg is greater than Vp. So in the question, it is given dVp over dk is less than 0. So if you, that means it's a negative quantity. So if you put it here, this will give Vg is Vp minus k dVp dk. So here you can see that Vg is less than Vp. So that means it's following a normal dispersion. So there are different conditions for normal dispersion. One is this, and then one is dn over d lambda is less than 0. Now we got another expression, dvp over dk is less than 0. So always remember this and this. Okay. For normal situation, groove velocity is always less than the phase velocity. If we have an anomalous part, anomalous dispersion, then the groove velocity is greater than the phase velocity. Okay. So is it clear? Okay. So I think this is all about week 2. We'll meet on next live session to solve the next 2 problems for this week and to see what is there in week 3 and to solve the problems of week 3. So thank you for joining the session. I hope the problems and the questions are helpful to you to solve the assignment or to clarify your doubts. So we'll meet on next Tuesday for same time from 6 to. So try to join the session and try to clarify your doubts as much as possible. Okay. So let's meet on next Friday. Sorry, next Tuesday. So thank you. Goodbye, everyone.